Swayam Prabha. Digital India. Educated India.
So in connection with these involutes of a circle, which are very important for fashioning these so-called involute gears, the involutes of a circle which are in the form of spirals, they are also used to form what are called as or fabricate what are called as spiral compressors or scroll compressors. Okay, so basically, so that is another important application, and so let me just say something about that. So there are these. So there are involutes of a circle. You can one of the things you can make using this is the so-called scroll compressor. So basically what happens is that of course if you take a circle and then you draw the involute, you will get at any point you will get a spiral like this. Okay, and what you do is that you take two such spirals. Okay, they are not really spirals in the sense of mathematical spirals. There are different types of spirals and they have different mathematical equations. And of course, you take any curve, it has a mathematical equation. If you take a parallel curve, it will look like that, but mathematically it will be different. So there are many curves which you look spiral-like, but they may not exactly be spirals of the same type mathematically. But in this case we are only looking at the spiral type of curves which are involutes of a circle of fixed radius. And then what you do is that you take two of them. So you see, you take two of these these spiral things, and I'll draw another one in a different color. So you see something like this. And the point is that you keep one of the spirals fixed, okay, and move the other spiral so as to touch this first one. Okay, mind you, these are all they are all constant width, and because they are all going to be parallel. All right, and what will happen is that if you fix one and move the other, then the amount of area trapped between two successive points where they touch, as one of them rolls on the other, that area kind of becomes smaller and smaller and smaller as you come from outside to inside. So if this was the cross section of two spiral-like cylindrical surfaces. Okay, so you take a surface which is generated by this spiral, by passing lines normal to the plane of the diagram. Okay, so it's a sheet, whose cross section looks like this spiral, and you put two such sheets and then roll one on the other. What will happen is that anything outside, for example, a gas can be trapped inside, and as it rolls, it will be pushed inside, and the volume that is being occupied by the gas is made smaller. So this is used to make gas compressors. So this is very, very important for gas compression. And so the important thing is that you are using involutes of a circle, and two of them. Okay, so I can show you a picture. So here is so here it is. So you see, you have the red spiral which is fixed. Okay, and then there's a black spiral which is moving around. And if you look at it from the outside and you start going inside the spiral, you see that the area that is trapped, is becoming smaller and smaller and smaller. Okay, and therefore the same amount of substance is constrained to go into smaller and smaller volumes as it goes from the periphery to the inside. And finally, at the center, it would have been, compressed a lot. And so, if the gas was outside in the periphery, then what you get from inside is a compressed version of the gas. Okay, and then you can repeat this several times, and it is used in gas compression. Okay, so this is one important application of involutes of circles, apart from involute gears. Okay, now what I want to next talk about is when talking about involutes and evolutes, the most important curve in algebraic geometry is that of a cycloid. Okay, and the cycloid is a solution to several problems. So I just want to mention it. The importance of a cycloid. Okay, so you see, so the first thing is geometrically, you see the cycloid is obtained by rolling a circle on a line. Okay, and looking at the path traced by a point on the circle. Okay, so basically, if I draw it like this, so I start with the circle here. So this is and I start with this point here, and then it starts rolling like this, and then I will get a curve like this. Okay, I'll end up with a curve like this, and you see at this point, you see you will have the maximum height of the curve, and that will correspond to this point P moving all the way to the the other vertical end. Okay, and then you see you get this you get this cycloid. Okay, now you can write out mathematical equations for it, and all that can be done. But what I want to say is that so there are things that I'm going to say, which you can actually write down mathematical equations, and you can verify. But the geometry is what is very beautiful. Is that, see, the first thing is that so at this point, if you draw the normal, these 2 points are actually cusps. This point and this point. Okay, and if you had moved the circle in both directions, you will get the next branch of the cycloid. The next branch of the cycloid here. Okay, and then before this, you would have got the other branch here, like this. Okay, and so this is a curve that will sit on the line. Wherever it touches the line, there will be cusps. Okay, and the interesting thing to note is why you get a cusp there. What will happen is that if you write down a unit speed parameterization, or even at least a unit speed parameterization will be, it will be guaranteed between these two cusps. Okay, so if you write down the parametric equations, you will see that at those two cusps the curve is not regular. Okay, but to either side of a cusp, you take the unit speed parameterization and look at the the curvature vector. Okay, what will happen is that you will see that, for example, if you look at the tangent vector, okay, or the sine normal vector, you will see that it will start spinning, okay, at very high speed. Okay, so at the cusp it behaves in a very funny way. All right, and so that is one important thing. The other important thing is that for this curve, if you take if you take the evolute, okay, then interestingly you will get again the same cycloid. Okay, and when I say the same cycloid, it is up to a translation. So what will happen is that So let me show that. It will be like this. If you take the evolute, I will get a cycloid like this. You see, you will get a cycloid like this. This will be the evolute. So this will be the evolute. Okay, it will be just the the same cycloid, but translated vertically down, and then by a length which is equal to the diameter of the circle, and then left by a length which is equal to half the arc length of one complete revolution of the circle on the cycloid. Okay, so which will be half the perimeter of the circle. Okay, so you see so you can say that if you don't want to distinguish a curve and its translates, or you don't want to distinguish a curve and any of its rigid motion equivalents, then you can say the evolute of cycloid is again a cycloid. Okay. On the other hand, if you take the involute, involutes, you can take many involutes. So you will get all the involutes will be parallel curves, and only one of them will give you a cycloid. The other things will look like a cycloid, but they are not cycloids. So if you take the involute, what happens in this picture? So you will get, so I will need to rub this out. So let me rub this out. So you see what will happen is that you will get this. So if you take an involute, so I take, the way you take the involute is that you take this piece of thread from here to here, and you pull it out. And what you think you will get is again, you will get again, you will again get the same cycloid back. So interestingly, you will get this cycloid. Okay. Okay. So this is the involute you will get. This is the involute you will get if you pull out the string from this topmost point. Okay, but if you pull out the string from some other points, you will get parallel curves, but they will not be cycloid. So for example, I could have pulled out say, let us say this portion of the string from here to here. I could pull this out. Okay, and if you do that, I will get a curve like this. Okay, and the important thing is this is not a cycloid. It's not a cycloid. Okay, and similarly, of course, you could have done it somewhere else. So let me show you one more. I could have also pulled out something from here. If I pulled out this portion of the string, say from here onwards, this green portion, and then I will get something like this. Okay, and the point is that this is also not a cycloid. Okay, so these green and red ones are not cycloids. It's only the purple one that is the involute, which is a cycloid. Okay, so this is what happens with. So these are all things that you can of course verify. So the important exercise to verify is that you write down the parametric equations of a cycloid, and then take its evolute, show that it is again a congruent cycloid. Okay, and then you take the parametric equations of a cycloid and take the involute at this topmost point. Okay, then you will see that again you will get a congruent cycloid. Okay, and this can be mathematically verified. So I leave it to you to do that. Okay, it's a simple verification. And of course, it's easy to do because you know how to write the equation of the involute, you know how to write the equation of the evolute. So it's just a mathematical calculation, which I want you to do and verify. Okay, so that's what you get. Then now I am particularly interested in the connections with physics for this cycloidal shape. So the first connection is that this you take this. You take this cycloidal shape, and then you invert it. Okay, then you so basically it is like, you have a line, and then you have a circle that is hanging on that line, and it's hanging by that line, and it is rolling on that line in a hanging manner, and then you take a point on that circle which is rolling on that line, but it's hanging. Then again you will get a cycloid, okay, and now but the cycloid will be cup shape. So you just do it like this. So let me draw it like this. So this is this a circle here, and then I'll draw this line, and so I will, as I trace this point, as a circle rolls like this, okay, and it's you imagine it as hanging, for example, think that the line is has some magnetic property, and the circle is a magnetic material, so that it is always held to the string, okay, or the line, so that as you move it, it will keep touching it. So if it rolls, of course it should not slide, it should only roll. Then you will get this, you will again get a cycloid like this. So from here to here, okay, I will get this this inverted cycloid shape, okay. And what is beautiful about this curve is, this curve is the unique curve which is called a tautochrone, okay. So if you take this portion of the curve, so let me show this portion of the curve, starting from this point, let us say A, to this lowest point B, okay. You take this portion of the curve. This portion of the curve is the unique solution to what is called the Tautochrone problem. So the Tautochrone problem is that you are in a vertical plane. The idea is the following. The idea is that, you see, you want to find a curve. Oops. So you want to find a curve so that no matter where you start, okay, on the curve, and you drop something, when the object is moving along the curve, then it will reach the bottommost point, at the same amount of time. So basically, the problem is that you want. So I start with the bead here, okay. So think that this is a bowl with cross section, this curve, okay, or more generally, you take. So let us do the following thing. You simply take any curve, all right, and it can be of any shape, but let me only worry about the movement from the, let us say, the topmost point to the bottommost point. So let me take it like this. So if I take the point A and if I take the point B, what I could do is I can draw several curves like this, okay. And the question is that you take each of these curves. So suppose I choose one of these curves, let us say the curve C1, okay, and I place an object here, let us say P at P1, and then I let it to slide down along the curve, okay, under the influence of gravity. Then this P1 will arrive at B, and the time taken by P1 will be some value, okay. Now if I instead of starting at P1, suppose I start at P2, okay, I look at the time taken by P2, okay. So this is the time taken to arrive at B from from P1, okay. Similarly, if you take at P2, I can measure the time taken to arrive from P2 to B. So the way you imagine it is that along this curve C1, you think that there is a frictionless string, and you're allowing a frictionless bead on it to travel along that, and it's only under the influence of gravity. So you have gravity here, And the point is that, of course, it's obvious that how much time it will take for the bead when it is released from a point on the curve to reach the lowest point. That will depend on the nature of the curve. It will also depend on so I should say where you started from. Okay. So if you started at a certain height, if you started at a certain height on different curves, okay, then anyway, that the time taken may be different. Or for that matter, even if you started at the same arc lengths on different curves, okay, measured from the lowest point also. There is, in general, the time taken to reach the lowest point depends on the curve as well as the starting point. Okay, but the question is, you want a curve for which it is independent of the starting point. Okay, find a curve with the following property. The curve passes, the top end of the curve starts at A, and the bottommost end of the curve ends at B. And the curve should have the following property, physical property. You take any point on the curve and you release an object constrained to move down the curve only under gravity. From that point, the time taken to reach the lowest point is independent of the starting point. Okay, so such a curve is called a tautochrone. Okay, and this is called the tautochrone problem. And interestingly, the solution to the tautochrone problem is this arc of the cycloid from A to B, with A as the cusp. Okay, and B is the the lowest end. All right. So the solution. Let me say that you want a curve such that Tp is independent of P. Okay, and the solution is a cycloid as above. So this portion of the cycloid, that is the solution. And that is the only curve that will do this. Okay, so this involves writing down some equations of motion, and you have to use some kind of optimization to check it. Okay, but it involves only some basic calculus and some basic physics. It can be done. Okay, so you can try to do it. But what is important is that this cycloid is the solution to the tautochrone problem. And the word tautochrone means tauto means same or equal. Okay, and chrone is of course time. Chronos is time. Okay, so irrespective of where you start, you will end up at the bottommost position at the same time. If you imagine several particles starting at different points of the curve, but at the same instant of time, they will all reach the bottommost position at the same time. That means the slower the particles that are closer, okay, they will go slower. The particles that are further away, they will come faster. But somehow the curvature of the curve is adjusted in such a way that no matter where you start, they all end up at the bottommost position at the same time. Okay, so again, there is a a nice picture I want to show you. It's not here, sorry. I had so here it is. So here is a nice picture. So you can see that all these, there are 4 beads, blue, red, green, and yellow. They all start at the same point of time. Okay, and they all meet at the lowest point. That is, they take the same amount of time, and you can see the velocities are plotted in a separate graph. Okay, so this is what happens, and this arc that you are seeing is the inverted cycloid from the cusp to the topmost point, which becomes now the bottommost point. Okay, so this is also the solution of the Tautochrone problem. So the solution is a cycloid. So for the Tautochrone problem, the solution is a cycloid. So in fact, if you take this, if you take this full cycloid here, and make a bowl out of it, okay, you take this full cycloid here and then rotate it to make a bowl, okay, then you get a what is called a tautochronous bowl, and on that bowl you at any point you place beads and at several points and release them. They will all come to the bottom of the bowl at the same time. Okay, that will happen. So it's a very beautiful surface. It's a tautochronous surface, as it is called. Okay, and so it's so the point is that cycloid is the solution. Okay, then let me come to the Brachistochrone problem. So that is also another beautiful physical problem for which again the solution is a cycloid. So the Brachistochrone problem. So here brachistos is supposed to be quick, chronos is of course time. What happens here is, again you have a point A and you have a point B, okay, and you are trying to find a curve. You can draw many curves. I can draw, and the idea is that I have an object here at A. It's moving to B. I want it to move from A to B under the influence of gravity. Okay, and there is it is constrained along a curve. Okay, and what I want is I want to find a curve C, so that the time taken is the total time taken is minimum. Okay, so there is a curve. So here, if this is C, TC is equal to total time taken. Total time taken to go from A to B. Okay, and so the problem is find C so that TC is minimum. Okay, and so the shortest time should be taken as you move from A to B, and the shortest is Brachistos, and time is of course chronos. So this is a Brachistochrone problem. Interestingly, the solution of this problem is also a cycloidal curve. Okay, and one would think of curves like this. For example, you can think of just naively a straight line movement like this, or you can think of something like this. You go vertically down, have a small bend, and then go out like this. And interestingly, very counterintuitively, these are the worst. These are the worst examples. The only curve that will work will be the cycloidal curve with a cusp at A. Okay, an inverted cycloidal curve with the cusp at A and passing through B. That is the only curve that will work. It has to have a cusp at A. That's right. The cusp has to be at A, but the B is now constrained. See, there in the Tautochrone problem, the B was the lowest, but here B is not the lowest. So it's only you have to find here the cycloid has to be fixed in such a way B need not be the lowest point. So you look at all cycloids with cusps at A and choose only that cycloid which passes through B. That is the solution. Okay, look at all the cycloids with cusps at A, inverted cycloids, and choose only that cycloid which passes through B. That is the solution. And again, the solution is again a cycloid. Solution is again a cycloid with cusp at A, okay, and through B, okay, and of course in all these cases the particular cycloid is unique. It's uniquely determined. And again, I can show you another interesting picture. So I think here it is. So you see here is this. So you can see it's quite interesting. The straight line path is the slowest. Okay, the bead that is moving along the straight line from the topmost point to the bottommost point is the slowest. Okay, and the bead that vertically goes down then bends off and then moves horizontally is somewhere in the middle. But the fastest is the one that moves along this red cycloid. Okay, and that is you see that is a unique cycloid with the cusp at the top point and passing through the bottom, passing through the point at the bottom. And what is important is you notice that the point at the bottom is not the point at the bottom, is not the bottommost point of the cycloid. Okay, so this is the Brachistochrone problem. Okay, and if you naively think, it looks very counterintuitive. All right, so this is one important thing. Then there is yet another place where the cycloid is important. It's in the so-called cycloidal pendulum. Okay, so what you do is that, so let me tell you about that. So cycloidal pendulum, and this was due to Christian Huygens. So you see, so he was the one who, for example, advocated wave fronts. And his theory of wave fronts was built on the theory of involutes. Okay, and therefore he was trying to solve this problem that if you have a simple pendulum, then when you write the time period of the simple pendulum, then you see the time period is independent of the amplitude of oscillation only for small oscillations. It's an approximation. So that means that if there is going to be large oscillation, then it will not keep time. All right. So what you do is you are in some kind of trouble if you want to measure time in a situation where you cannot avoid large amplitudes. For example, you put a pendulum on a ship which is rolling or a boat which is rolling over the waves. You cannot stop it from, you cannot stop the pendulum from having large amplitudes. Okay, and then once the amplitudes are large, then you are in trouble, because then the time period of the pendulum is not independent of the amplitude. So the question is, can you do something so that you can get a pendulum which, irrespective of the amplitude, the time period is always independent. It's independent of the amplitude. And the answer is again, this beautiful picture of, you take a cycloid and take the special involute, which is also a cycloid. So the picture is like this. So you have the original cycloid like this. So let me draw this. So you have the original cycloid. Okay, and then you have its involute. So the involute will be, so if I take at the topmost point, I'll again get a congruent cycloid. Okay, so this is the involute. So now what you do is you just invert this diagram. So if you invert this diagram, I will get something like this. So you draw it like this. Let me put it down like this. Okay. Then I will draw the involute like this. Okay. And here is your cycloidal pendulum. What you do is that you take this point and you suspend a mass, a string, and with a mass here. And the point about this is that these edges, which are parts of the cycloid, they will constrain the string as it turns, as it swings. So for example, if the string were, if it were to move, let us say to the left, then say up to this point it moves, and then this portion of the string is stuck to the the cycloid, and only this portion is kind of is free. Okay, and the point is that this gives rise to a what is called the cycloidal pendulum. And the important thing is the time period is independent of the amplitude. And the amplitude is how far it swings in both directions. And for an ordinary simple pendulum, that's completely false. If the amplitude becomes very large, the time period will start heavily depending on the amplitude. Okay, and the thing is to constrain the movement of the pendulum on two sides by obstructing it with inverted cycloids, and then you get a cycloidal pendulum. And so that means that if you have several pendula which are having different amplitudes, they will all maintain the same period of oscillation. Okay, so these give rise to what are called as isochronous pendula. And of course here isos means equal, chronos is time, so they all have the same time period. Okay, this was invented by Huygens, and I can again show you an interesting picture. So I have it somewhere here. Where was it? Here it is. So here you see, here there are 5 pendula which have different amplitudes. Okay, but you can see they all keep the same time, and you can believe that again you see the cycloidal shape is very, very important. If you take a simple pendulum, the arc along which the pendulum, the bob of the pendulum moves is actually arc of a circle, but here the arc is the arc of a cycloid. And also the string of the pendulum, that is also constrained on both sides by portions of the cycloid. Okay, but that is what gives it the isochronous nature. Okay, so in principle, if you use such a pendulum even on a ship, it should keep correct time. But history has it that trying to do this to put this theory to practice became very difficult. So people had to think of other things. But then the mathematical significance is that the cycloid appears. Okay, so you see the cycloid is kind of universal; it appears in all these cases. Okay, so that is something that I want to tell you. Of course, one can write out the physics, the math, the equations, and verify this, and show that in all these problems, whether it is the isochronous pendulum problem or the Tautochrone problem or the Brachistochrone problem, in all these cases, the solution is only a unique cycloid. Okay, so that is and the beauty of the cycloid is it is its own evolute, and if you take the right involute, it's again a cycloid. Okay, so that is the importance of cycloid. Now, finally, I would like to mention, one other important fact, which is in connection with the Hopf-Zumlauf sides. Okay, and that is the plain version of what is called the Gauss-Bonnet theorem. Okay, and so let me just make the statement. Okay, so generalization of Hopf-Zumlauf sides. It's called the Gauss-Bonnet theorem for curved polygons in the plane, and So what is this? So basically what you do is that you look at a polygon in the plane which is curved. So you are looking at something like this. Okay. So you have, so I will call the vertices of the polygon as P1, P2, some Pn, okay. So Pi, and maybe I'll just put a last vertex before it. So this is a polygon, okay. So you see, this is a polygon which is formed by taking, instead of the sides being straight lines, you put curves, okay. And then what happens is that at every vertex of the polygon, and of course you put an orientation, you put the standard positive orientation, all right. Then at Pi, you have the notion of an interior angle and an exterior angle. So basically what you do is that, at Pi, you can look at the incoming tangent direction, and then there is the outgoing tangent direction, okay. And then there is this angle, which is, maybe I'll call this as some beta I, okay. This is the exterior angle. And then you have also the, interior angle, which is alpha I. So alpha I is the interior angle, and beta I is the exterior angle at Pi, okay. Now the question is, what is the Hopf-Umlauf-Sachs? It says that if you take a simple closed curve, smooth curve, then the total curvature is plus or minus 2 pi, okay. Now this is a generalization of that. The question is that now what will happen to the total curvature, okay. So the statement is the total curvature, so I should say signed curvature, okay, as you traverse this curved polygon once, all right. That will be that will simply be, the sum of the interior angles. So this is the sum of the interior angles, okay, minus n minus 2 times pi, okay. And the simplest case you can think of is when it is a curved triangle, okay. If it is a curved triangle, and if it is actually, if the curves and the boundary of the triangle are actually straight lines, then the total curvature, sine curvature will be 0, okay, because along a straight line the curvature is 0. And when I say total sine curvature, mind you, you have to add the curvature, but because this is piecewise smooth, you have to add the curvature on each polygonal curve, and you have to take the sum, okay, because on each smooth piece of the curve there is a turning angle, okay, and the sine curvature is defined, okay, because orientation is given. So you can add the total curvature for each arc, each closed arc, which corresponds to a curved side of the curved polygon, and you have to add all of that. Of course, if all these arcs are straight lines, then all these are going to be 0, right? So the left side will be 0. For that matter, not only for a triangle, for any ordinary polygon, the left side is 0. And what is the right side? The right side is 0, which just recovers the fact that the sum of interior angles of a polygon of side with n sides is n minus 2 pi. If you put n equal to 3, it's a triangle. The sum of the 3 interior angles of a triangle is 3 minus 2 pi, which is just 1 pi, which is pi, okay. So this is a generalization of that, okay. And the way to prove this is you can deduce it from the Hopf-Umlauf-Sachs by smoothing out at every vertex. So what you do is that you construct another, you have to just compare it with another curve for which you can apply the Hopf-Simulov-Sats, and that curve will be, at each of these, vertices, you just smooth it out like this, okay, and so you smooth it here, and here also you smooth it out, and you keep doing this. Then you will get a red curve, which is only the same as the original blue curve, but only at the sharp corners you have smoothened it out, and for the red curve the Umlauf-Sats applies. Then you have to worry about what happens at each vertex, and if you look at what happens over this closed curve, okay, and you let these two tend to 0, then you will get only the contribution due to the change in the tangent direction, okay. So you have to use that limiting process, and if you write it down, you will get this very beautiful result. So it is just a result of the Hopf-Simulov-Sats, okay. So this is the Gauss-Bonnet, and it generalizes for if you take a polygon, standard polygon which is made up of straight line segments, then the sum of the interior angles is n minus 2 pi, okay. If it is not made by straight line segments but by curved lines, then the sum of the interior angles minus n minus 2 pi, that difference will be the total sine curvature. That's what it says, okay. So this is an interesting theorem. So I think you can write out the proof, it's not very difficult, by using the smoothing argument, all right, and applying you have to apply the Hopf-Simulov-Sats, and that's why it's a generalization of the Hopf-Simulov-Sats, okay. So I think I will stop here, okay. So all the best.